Welcome to The Explainer. Today we're tackling what I like to call the public health paradox, individual versus population risk. We're going to completely flip how you think about danger, disease, and the hidden math behind them. So let's jump right in.
Okay, I want to challenge your intuition right off the bat. Think about this. What is the bigger health threat to society as a whole? Is it a highly lethal, deadly genetic mutation, or just everyday, mildly annoying ambient air pollution? Now, your gut reaction is probably screaming that the deadly mutation is the ultimate threat, right? But to get the real answer, we actually have to look at the math through two totally different lenses.
First up, let's establish our baseline by zooming in on the individual level. We have this really fascinating concept called the attributable risk fraction. Some folks also call it the attributable risk percent among the exposed. Basically, this isolates the specific group of people who actively have a certain risk factor. It tells us the exact proportion of disease cases within that specific group that was directly caused by the exposure. This is absolutely crucial because it shows us exactly how much disease we could completely prevent if we just wiped out that risk factor entirely.
To wrap our heads around how we actually find that fraction, let's look at a concrete number, 5. Let's say heavy smokers have a relative risk of 5 for developing a specific type of cancer compared to non-smokers. That means they're literally 5 times more likely to get sick. But here's the million-dollar question. How much of that cancer in the smoking group can we blame exclusively on the smoking itself?
Well, let's play medical detective for a second and isolate the exact proportion of blame. It's actually a super simple mathematical formula. Step 1, we take our relative risk and subtract 1. So 5 minus 1 gives us 4. Easy enough. Step 2, we divide that total by our original relative risk. 4 divided by 5 gives us 0.80, or exactly 80%.
And honestly, this brilliantly illustrates what that math actually means in the real world. If a clinician is sitting there in an exam room, that 80% represents the cancer cases among their heavy smoking patients that are specifically directly due to smoking. The other 20%? Well, those cases would have occurred anyway due to baseline genetics or just random factors, but the smoking, it's entirely responsible for that massive 80% chunk.
So, the key takeaway here is that a doctor cares deeply about the individual patient sitting right in front of them. And that's exactly what attributable risk is for. But what if you're an epidemiologist? What if you're trying to evaluate an entire city or even a nation? You have to zoom way out. You have to pivot to what's called the population attributable risk fraction, also known as the population attributable fraction.
Here's the difference. While the standard attributable risk fraction only looks at the folks who are exposed, this population metric evaluates the entire community. It inherently includes everyone, both the exposed and the unexposed. So, if a harmful exposure is completely eliminated from everyone, the population attributable fraction represents the exact percentage drop in the total community-wide disease burden. It's the big picture.
Now, to understand how this builds, we have to look at two independent variables that really drive this population metric. First, the strength of the risk factor itself, which we measure by relative risk, and second, how common that risk factor actually is in the general public, which is known as the prevalence of exposure. Think of these as the twin drivers that determine the overall health of a society.
Let's actually lock in the definition of that second driver real quick. Prevalence is simply the number of existing cases or exposed individuals in a population at a specific moment in time. I know, it sounds incredibly basic, right? But prevalence acts as this crucial multiplier. It completely changes the narrative when we scale things up to the population level.
Which brings us right back to our initial question, the public health showdown, lethal mutation versus ambient air pollution. On advanced epidemiological exams, a critical clinical distinction comes up when comparing a rare but highly dangerous exposure against a mild but ubiquitous environmental factor. Let's see how prevalence completely flips our understanding of what's truly dangerous.
Imagine a rare genetic mutation, and this gene is absolutely devastating. It gives carriers a massive relative risk of 100 for developing a severe neurological condition. Just think about that. If you have this gene, you are literally 100 times more likely to get the disease. For that specific person, the individual attributable risk fraction is near 100%, meaning their illness is almost certainly caused by that exact gene. But here is the catch. The prevalence of this mutation is exceptionally rare. It only affects 1 in a million people. So while the risk to the specific individual who has it is catastrophic, the population attributable risk fraction for this mutation is practically 0%. Why? Because eliminating it would save almost no lives across the general public as a whole.
Now, let's contrast this with ambient air pollution. Breathing slightly polluted city air might carry a very modest relative risk of only 1.2 for respiratory illness. I mean, compared to a relative risk of 100, 1.2 seems like absolutely nothing, right? It barely even registers as a threat on the individual level. But here is where the math catches up with us in a big way. Because every single person in the city steps outside and breathes that exact same air every single day, the prevalence of this exposure is a staggering 100%. The entire community is in the exposed group, no exceptions.
When we put these two threats side by side, the paradox totally reveals itself. The lethal mutation has this massive relative risk of 100, sure, but its near zero prevalence completely neutralizes its impact at the community level. On the flip side, air pollution has a tiny relative risk of 1.2, but at 100% prevalence, the population impact is massive. High prevalence creates a massive population attributable fraction.
So, if you take away nothing else from this explainer, remember this. A weak risk factor with high prevalence can have a far, far greater public health impact than a lethal risk factor that is exceptionally rare. Finding a cure for that rare gene, that's a literal miracle for that 1 in a million family for sure, but it does almost nothing for the city's overall disease burden. Conversely, rolling out clean air initiatives, that's going to prevent thousands of total hospitalizations citywide, simply because it drops the risk for every single citizen.
And this perfectly illustrates how these math fractions dictate completely different approaches in medicine and government. Clinicians treat the individual. They rely on the attributable risk fraction to look a patient in the eye and tell them exactly what's causing their illness. But mayors and policymakers, they treat the city. They rely on the population attributable risk. When you're looking at a dashboard of millions of lives, prevalence is the ultimate factor that truly dictates public health policy.
Which brings us to a final, pretty provocative thought. Think about it. If you controlled your city's health budget, would you fund the cure for the rarest, most lethal disease, or would you spend it to clean up the most common, mildly toxic environment? Understanding the real difference between individual and population risk completely changes how we answer that question. Thanks so much for joining me for this explainer, and I hope this leaves you thinking deeply about how we as a society really prioritize risk.